So this is a short lecture on lighting. Um, there are a few lighting design goals, at least as I see it, and certainly this is something we could discuss. Um, I think it's important to provide sufficient light for a variety of daily functions. My goal with energy efficient building is to use as little electricity as possible. That may mean use daylighting, but it may not. And it's important to minimize glare and discomfort. And in the case of daylighting, thermal gains losses. And in the case of electrical lighting, there can often be thermal gains that are undesirable. Um, so the simplest thing, the staple of all utility energy efficiency programs, has been switching out incandescent lights for compact fluorescent lights. And that's been the case for almost 20 years now that compact fluorescent light has been available as an option. And obviously, if you can get the same amount of light for a quarter of the energy, then why wouldn't you do it? Um, well, one thing you need to do is when we say what same amount of light, well, what is this amount of light? Because people certainly, almost certainly, your parents and probably you, even now, when trying to think about what light bulb to buy, we have lived with incandescent lights for so long as a culture, for uh, almost for more than a century anyway. So the idea of a 40-watt light or a 60-watt light or a 100-watt light means something to people. They have a sense of what size room you would put a light bulb in that were of that particular wattage. And what we need to do is accustom ourselves to thinking in terms of lumens, or at least that's how the Department of Energy has been trying to get us to think about things. So, for instance, a 60-watt light bulb has roughly 800 lumens in a traditional incandescent light bulb. So we should want to buy an 800 lumen light bulb, and hopefully it supplies those lumens with fewer watts than 60 watts. So for instance, the lighting facts, which you now see on light bulbs, which are like nutrition facts, they're modeled on the same thing. I think it's the same font even. Here we have 870 lumens. Um, and and then we have the number of watts energy used is 13 watts. And we're going to get into the light appearance, whether it's warm or cool, and that is in kelvins. And so 2700 Kelvin is what we have, as a culture, have gotten used to with incandescent lights. Um, so that's the idea has been handed on down. So an incandescent light, what is the efficiency of incandescent light? Well, we talk about it not as efficiency, but of efficacy, which is how many lumens do you get for each watt. This is quite easy, and having had a discussion about efficiency, we know the thing we want is lumens, the amount of light, and the thing we have to supply, our input is watts. So here we have one 820 lumens, a 60-watt light bulb. The efficacy of this incandescent light bulb is 13.66 lumens per watt. Compact fluorescents, which by now probably everybody is familiar with, I don't have to explain them. You get a similar amount of light, so 870 lumens, and this one uses 13 watts, so that's 66.9 lumens per watt. Much, much higher level of efficacy. Um, there are now LEDs available, and something you're going to see is that LEDs are changing so fast. They are the industry has just grown by leaps and bounds and developed the technology. So, for instance, the technology that I'm showing you on this page, just 2 years ago, I was blown away with this new light. It was the best thing, and I bought a few myself. And I took one apart, and you can kind of see how they solved this problem. So here's here's one where the light output is 800 lumens, about like a 60-watt light bulb, and it uses 12.5 watts. So, what is the efficacy of of this light? Um, if you look here, 870 lumens for 13 watts, and here we have almost 13 watts for slightly fewer lumens. So the efficacy of this LED light bulb is not any better than a compact fluorescent. But we can get into what it looks like a little bit more. So, for instance, there's a color rendering index, and some lighting facts will have that and some don't. Generally speaking, a regular old-fashioned incandescent light bulb has a color rendering index of 100. Interesting that it was set at the light bulb that we grew up with, that our parents and our parents' parents grew up with. That's color accuracy. Well, of course, that's not actually necessarily color accuracy. It it's based on a cultural perception and the idea that people don't want things to look different. Um, so that same company, just a year later, created yet a different light bulb, and so I'll go back for a second. So what was really brilliant about this Philips L1, I think, or L Prize light bulb that has this yellow thing is when it's turned off, it looks like it's just got these orangey yellowy things on, and when it turns on, it looks like the white that we're used to with an incandescent light bulb. And the reason that they do that is called a remote phosphor. And so the normal LED engines have a very, very blue light, and you can see that here. So the remote phosphor is essentially a filter to change the color of the light as it goes through. So it's a remote phosphor. Well, just a few years later, they come up with a different one. This one, it doesn't look. It looks more normal. It does. You don't see that yellow remote phosphor on it. And in fact, it also had better efficacy. So now it's 830 lumens and it's using only 11 watts. So that's an efficacy of 75.5 lumens per watt. And it fits neatly in all the various places where you in the past would have put an incandescent light. And that was not always the case with compact fluorescent light bulbs or even with higher power LEDs up until this time. So if you take this one apart, you see it also has a remote phosphor, but it's hidden under that other lens. And so this has uh, fewer LEDs, and what it's doing is instead of putting them all around the bulb in kind of columns the way the previous iteration had, this one they've got this kind of remote phosphor cap that also redirects the light into a not quite 360-degree angle, but it redirects it more evenly, which is again more like what we're used to with incandescent light bulbs. And here it is on with the cap removed, and you can see it's very, very blue. And so you put the cap on, and you get that white light that we're used to with an incandescent light, and then you just put the cap on. Well, then Cree, which is another LED company that's competitive, also comes out with another light bulb that fits the form factor that we've gotten used to with the old-fashioned incandescent light bulbs. So again, we get 800 lumens. It's meant to replace a 60-watt light bulb. And the energy used now is only 9.5 watts, and we've got an efficacy of 84.2 lumens per watt. So it's really, really getting much more efficacious. And this is a product that has only been available for a year or just over a year, and yet it is already out of date. The newer ones have a much higher Cree, or color rendering index, which is just remarkable. So this Cree light bulbs takes a different approach. The LEDs here are put around a heat sink. One thing about LEDs is that if they overheat, they don't work very well, and they degrade very quickly. So the big challenge with manufacturing LED light bulbs is uh, to to have a heat sink where the heat from the LEDs can be dissipated. And of course, there's a lot less heat generated overall because more of the energy going into the light bulb is is being turned into light instead of heat. With the incandescent light bulb, most of it is just coming out as heat. Um, and so you see that as you try to get brighter and brighter, higher lumen light bulbs, you end up having to put in more and more high power LEDs. And so at 22 watts, this light bulb, which is meant to replace a 100-watt light bulb, the ambient LED um, is no more efficacious than a 23 watt compact fluorescent light bulb. So there's still room for improvement. Uh, there's still areas where the industry is growing. So one of the choices that you'll have now that you never really had back in the old days of incandescent lights is that you need to actually choose the color temperature for your application. So for most residential applications, 2700 Kelvin, possibly up to 3000 Kelvin, is what people tend to like. So the 3000 Kelvin in kitchens is often used, also in bathrooms. But generally speaking, people think of the home as a uh, um, the warm place, and so the warm white of the 2700 Kelvin bulb is what people have gotten used to with incandescence. Um, but if you think about uh, higher higher color temperature lights, so daylighting, for example, if you just have daylight, it's in the range of 500 to really 7 or even 800 Kelvin, depending on the time of day and what time of year. Um, so often supplementary lighting that is not meant to detract from or clash with daylighting. So, where you've got, say, daylighting at a window and you want to boost the amount of available light far deeper into a room, often it's wise to use very blue light so that matches daylight color temperature. This is usually an issue for commercial buildings and not for residentials. So I'd like to argue that this approach, saying we're just going to find the light bulb with the best efficacy and put it in everything the same as we always did, is not necessarily good lighting design, and that it's possible to have energy efficient lighting design. So the first thing lighting design has to do right is to provide sufficient light for a variety of daily functions. Well, what is sufficient light? Well, we need some units to measure that. So this goes back to candle power. You've probably heard of, you buy flashlights with a certain amount of candle power. So candle power was actually defined in England by the Metropolitan Gas Act of 1860 as the light produced by a pure spermaceti candle weighing 1/6 of a pound and burning at 120 grains per hour. Um, yeah. So what is spermaceti? Whale oil. Whale oil was the dominant lighting fuel from about 1750 to 1850. It burned cleaner and gave a pleasant light. It was much nicer than candos and tallow and wax. So the whaling industry, which to some degree is the reason that New England was prosperous in the first half of the 1800s, largely was to provide oil for lamp lighting. Um, Certainly, they also provided whalebone for corsets, but that's another story. So roughly, one candle power, as defined by the Metropolitan Lighting Act, is approximately equal to a candela, which is an SI unit. So 1 candela is equal to 1 lumen per steradian. A steradian is a measure of angle. So what's a lumen? So lumen is not really brightness. It is the luminous flux. It's the total flow of light from a given source. So, and then we know that a lumen is a candela per steradian. A candela is the luminous intensity, the flow of light in a particular direction, and a steradian is the beam angle. So that means that a candela is also equal to lumens per steradian. And this has an implication that we're going to talk about and demonstrate in class. But what we really are interested in is how much light, if this is about how much, getting enough light, whatever that is, to perform daily tasks. Well, where do I want the light? I want the light on a surface. I want the light on say, a work surface or on an object that I'm looking at or working on. And that is measured in lux. It is the illuminance or luminous flux density. So it's the amount of light falling on a surface, which in SI units is in meters squared. So 1 lux is equal to 1 lumen per meter squared, and a foot candle is 1 lumen per per square foot. An interesting other thing happens, which is 1 candela is equal to 1 lux times a meter squared, and this is the square of the distance from the light source, not the meter squared that it's falling on, but actually the distance from the light source. And that's going to be important later, and hopefully we'll demonstrate this in class. So a candela per meter squared is the luminance, the apparent brightness of a surface. So if we're looking at the brightness of a surface shining at us, and this is important for us to be able to measure if we're worried about glare. So remember that 1 candela is equal to a lux times the distance, the square of the distance. Well, remember that square of the distance creates an interesting effect, which is to say, so at 1 meter, 1,000 lux is what you get from a light source of 1,000 candelas. And as you go farther and farther away from that light source, this is intuitive, you've experienced this yourself, of course, as you pull say a flashlight farther away from the object you're looking at, it's not as brightly lit. So, but that difference happens in at an exponential rate related to distance. And so that means that if you were designing task lighting, for example, you can get a very, very high brightness by moving a light source close to the surface on which you're doing a task. So how much do we need? I think that this is something that we should open our minds to evaluating on more of a case-by-case basis. The human eye can work from 1/10 of a lux to 100,000 lux. Our eyes are amazingly able to adjust. And different countries have different requirements. So 1 lux is considered safe for emergency lighting in Britain, but in the US it's 50 lux. In the US we require 100 lux in hallways. And we're supposed to have 300 to 500 lux for most ambient lighting. And yet 500 lux is clearly enough to do tasks of even a fairly delicate nature. So do we have to make a whole room bright enough that we could do an intricate task anywhere in the room? I think that's a question worth asking. And for task lighting, you often see a requirement of 2,000 lux, which seems unnecessary. And humans, again, have dealt with considerably less light. So, clearly people did lots of studying and reading and writing and art by candlelight in the 1600s, and even in the 1800s. As far as I can tell in this picture, you have one candle sitting on the table. Candles were quite expensive, so light was really quite valuable. And you have people reading and sewing and doing needlepoint or whatever it is they're doing um, uh, in the 1800s. In fact, the availability of light has skyrocketed in human history. So, this is from a study done in 2006. Um, if you set the amount of light available per person in 1800 at 1, you can see that they had more light than they'd had a century before, and and centuries before that. That the wealth, say, of Europe, this mostly was looking at Europe. The wealth of Europe allowed them to uh, not only burn candles but also, again, whale oil. But then, as the Industrial Revolution took off, as whale oil was replaced with kerosene, which was both brighter and less expensive, and then finally as electricity replaced kerosene as the primary lighting source, you see a thousand-fold jump. And so per person, we now use 1,000 times as much light as our ancestors in 1800. And I just think that that is worth asking whether we need more light or whether we need to better place our light and use less of it. And that gets to what we need it for. So there are three basic lighting layers. There's ambient lighting, which is what you need basically to not trip over things, to see where you are, but you're not expecting to do detail work. There's task lighting, which is for reading, detailed work, cooking, makeup. Generally, 200 to 1,000 lux is recommended. And then accent lighting, which can be purely aesthetic. It can serve no function other than aesthetics, but it can also contribute to ambient lighting. It can be uh, defined uh, in various ways to contribute to ambient lighting. Um, but to know what we're doing, we have to have a sense of what it is. Again, this goes back to the recommendations for illuminances. So in the 1950s, this is in foot candles because this is America and they use foot candles. Um, but you can see the jump. In the 1950s, basically, uh, office lighting for regular tasks was set at 50-foot candles. Then in the 1960s, it jumps to 100-foot candles. And it stays there really until the 1980s when this was really the beginning of the first attempts at energy efficiency in the 1970s and 80s with the oil crises of that period. And you see recommendations for lower levels of lighting showing up. And we're pretty much back to where we were. I don't know that that means that 50-foot candles is what's actually required. Um, and it seems that it may not be the amount of light that's required, but simply the proportions of light. Let me explain what I mean. It's contrast. So we are contrast sensing creatures. We use, we also obviously use color, but we use contrast to sense the difference between, say, a predator in the jungle and the leaves around it. Um, I have found in the literature that there tends to be a ratio of 1 to 3 to 10 in terms of contrast that seems to work well uh, for lighting design. And that means that the task area should be about 3 times brighter than the immediate surrounding and 10 times brighter than the peripheral area. So that might mean that the task lighting should be 3 times the level of ambient lighting, um, and then as the ambient lighting dies away, or if you're going to say uh, accent lighting, that the accent lighting area can be uh, 10 times less bright than the task area. The key thing with contrast is that high levels of contrast strain the eye, but so do extremely low levels of contrast. So um, one way to reduce the number of lux required, so luminous uh, the luminance required, is to see if you can adjust all of the levels down so that the contrast remains at a good ratio. So I just thought I'd put this experiment up and let you look at it. So here's a rule of thumb ratio where I've set the different levels of gray at the percentages related to this 1 to 3 to 10. And I've got an eye chart in there, and you can look at that eye chart and see if it's easy to read. To me, that's pretty easy to read. This is the same scene, just 5% darker. And to me, again, easy to read and really actually a bit easier on the eyes. Now, it's also true that as people get older, we tend to need more brightness. So maybe, I don't know, 20 years from now, I'll find the previous one easier on the eyes than this one. Most of you are a good deal younger than I am, so it would be interesting to me to find out if you found this more comfortable or if you like the brighter one better. Here's what I would call an overlit ratio, which is where the surrounding area and the task area are so close that in contrast, or so little contrast, and the whole level is brightened up. And so this is kind of analogous to a room in which there's a lot of glare. And to me, that's hard to look at. And even though I can read the letters, I don't really find it very pleasant. And evenly lit, if it's evenly lit enough that you could do task work, to my eye, that is such low contrast and such high level of discomfort that I would consider that to be a bad lighting design. And also, you're now requiring a lot more light in this metaphorical room. But excessive contrast can also be a problem, especially where you have it in the peripheral area. So this area with the 400 lux that's outside of the 30 lux ring is also analogous to having a point of glare or a section of glare, and that can be irritating over a long time. So this is my kitchen, and I'm certainly not holding it up as a model of good lighting, but I had an interesting experience with the effect of lighting design. So one thing is that all the lighting in here is LED lighting, and I did this about 5 years ago, which means that I was paying $50 for some lights that you could now easily get for $20. And they also are going to last for 20 odd years, so I'm not going to do anything about it now. So we could discuss whether we like the lighting scenario, and I haven't turned on all the lights. This was just a picture I had handy, and obviously I could have moved the shop vac. But here's how it happened. So the kitchen was remodeled, but before it was remodeled, there was the original kitchen, which basically had two dome lights in the ceiling along this long kitchen, and of course they had incandescent light bulbs in there. So if you look at the number of watts that the original kitchen had, if you look at the installed watts, it was about 325 watts installed. Now, it also had a little fluorescent light over the stove. So typically you wouldn't have that light on over the stove, but you would have the two lights on, so that had two 60-watt bulbs in each of them. So now you had, so in typical operation, it was just under 250 watts. And when you were cooking, maybe you didn't have one of the other ones on because it's a longish kitchen, and so your operating watts at that point is I don't know what's that 130 watts or something like that. But the original lumens, right? So the original amount of light that was being provided by those lamps um, was, it was acceptable. The total installed was around 5,500 lumens available, which is certainly plenty. Um, but because I was organizing this new kitchen, so then the next thing we did was we installed compact fluorescent light bulbs. So we just swapped out one technology for another. And you can see that the blue line then, uh, roughly the amount of light available was roughly the same, but we dropped the wattage by 75%. That's the blue bars. So just installing new light bulbs gets you a long way. So under typical lighting situation and under the total installed, we've got less than 100 watts. We went from more than 300 watts to less than 100 watts. That's great. Good news. But it wasn't very pleasant lighting. It didn't serve the function that we want. And it seems to me that when you think about efficiency, you always want to think about what the function is going to be. So when we redesigned, we had more choices and more lights specifically pointed where we wanted them, but we also had the ability to turn lights off that weren't actually providing function. So the total installed watts was, even lower than the ones with the complex fluorescence. So that's great. We had about, I don't know, 75 total watts installed. But under typical operation, we were able to get away with about 20 watts actually operating. But when cooking, when doing an actual task, you could bump that up and you could light the countertops where you wanted the lights and turn other lights off. And so you had an operation of about 40 watts, which was the same as essentially less than one of the old light bulbs, the old incandescent light bulbs. But if you look at the red line, you'll see that when cooking, we have more total lumens available overall. So for the task lighting, we actually increase the available light. And when you look at that in terms of lux, you see it's even more dramatic. So for task lighting, we provide, I don't know, 525 lux for the task lighting. When we're just doing the ambient lighting, it's down around 70 lux. Around it, the accent lighting is a bit higher, but it's very specific. And so the average ambient, so when you mix all the bouncing of all these things, you get an average ambient lighting of about 100 lux, which is approximately what you had before in all the other circumstances, but you're doing it with a lot less energy and you're putting the light where you want it. That's why the task lighting is so much higher under the new design. So that strikes me as one possible design process that can work well, which is to start with the task lighting, find your lamp types, and then use that to find the contrast with the ambient level and make sure that the ambient level is sufficient for doing what you want, but that you don't want to overlight. And then accent whatever you want to accent, have your lights to create a pleasant environment. But once you've done that, you find that your accent lighting is contributing to the ambient lighting, and you may be able to drop the output of the ambient lighting lamps, the lamps that are specifically designed to do that. And that may allow you to drop the output of the task lighting because now the ambient lighting is lower. So in order to keep that contrast from getting excessive, you have to drop the task lighting. And you can kind of keep this in a feedback loop until you find something comfortable. So that's the approach I took. And in class, I want to do some experiments where you can get a sense of what looks good to you and how can you create efficient lighting, and we can figure out more than just the typical definition of lumens per watt for efficacy for lighting.